So far, we have introduced different basic operations we can use on relations, right, to design queries. And based on these basic operations, we can define more complex operations, which are also called derived operations. And in the following slide, we plan to talk about these derived operations for you. And the first one I'd like to introduce is for the set operations we can derive based on this union and difference. So we already mentioned this page before, right? We say this intersection and complement can both be derived based on this union and the difference. So the intersection denotes all the tuples existing in two relations, right? Which can be represented as this R1 cap R2, right? And for the intersection, it can be defined based on the difference, right? We mentioned before the R1 cap R2 equals to R1 minus parentheses R1 minus R2. I also gave you a exercise to prove this equation holds, right? Since it is defined based on the difference, therefore we also have some requirements for this R1 and R2 as inputs. So the R1 R2 should have the same schema, right? So this intersection can work on two relations with the same schema. This is a pre-requirement. As for the output of R1 cap R2, the output is also a relation, and this relation also has the same schema as the input, right? Besides intersection, we can also define some other derived operations. The most important one will be the joins. Join is a new operation we can define based on the basic operations. So formally join denotes a combination of two tables and also select some tuples meeting our requirements. How can we represent the joins? So we can represent the theta join first. It's a type of join with some conditions. Formally, we can represent theta join as like R1 joins with theta denotes a condition. Theta is a join subscript here. Theta joins R2, right? So the theta here is a predicate. In other words, it denotes a condition, right? And R1, R2, there are two input relations. So we have input schemas R1 with A1 to AN as attributes. We have R2 with B1 to BM as attributes. Then how about the output? The output will also be a relation, right? We can represent the output as a relation S. As to the attributes inside this S, we have A1 to AN and B1 to BM. We combine all the attributes in both R1 and R2. So what does this theta join means? And how to derive it based on the basic operations? So formally, we can define the theta join as sigma theta as a condition, and we're working on this R1 times R2. So you can see we do the product between R1 and R2 first, and then we can further do the selection on some conditions. This condition is defined by the theta, its predicate. Therefore, we say this theta is also a condition before, right? Because we use the theta here for sigma as a condition. We have sigma theta, the condition, which is a subscript, and parentheses. Inside the parentheses, we have R1 times R2 as a relation we're working on here. So therefore, when we are working on the theta join, we can take the product of R1 and R2 first, and based on the product relation, we can further apply this selection to select some tuples meeting our requirements. In this way, the output relation, the schema, the output relation will be much smaller than the product, right? Before we mentioned this product can be very expensive in both time and space cost. However, if we do some selections here, then we can shrink the dimensions, the rows in output, right? And columns still remain the same. It is the same as the product of this two relation, I mean the number of columns in the output. So for the C here, we can use all the conditions we defined before, right? It can return some Boolean values as a condition. So this is Theta Join. Theta Join is very important, and it can be very helpful for you because in the future, almost all the operations or the queries, we will be working on multiple relations and tables simultaneously. Then we have to join them together with the Theta Join to help us. So this is the definition of the Theta Join. You may also wonder, can we have any concrete examples so it will be helpful for you to follow the ideas, right? And we show the Theta Join example in this page. Let's assume we have two relations. The first relation we have is bars. We have a bar here. The bar has two attributes. The first one is bar name. The second one is the bar address. In the bar table, we have two tuples. The first one is ages. The second one is Michael's pub. Besides the bar, this relation, we also have the sales this relation. Right? The sales relation has three attributes: bar name, beer name, and the price. It denotes the price for the bars to sell some beers. And inside the table, we have four data tuples: the ages sells Bud, ages sells Miner, and Michael's pub sells Bud, and Michael's pub sells Corona. And we'll show the price for the beers, right, sold by the bars. And then we have a Theta Join query. We want to calculate the sales Theta Join bar with the condition the sales dot bar equals to bar dot name. In other words, we want to join the two tables together and also select the tuples with this bar name matching the sales bar, this name here. According to the Theta Join definition, we need to calculate the product between bar and sales first, right? By calculating this product, we will get another table. The table will have 5 columns we showed before, right? We know this number of columns will equals to 2 plus 3, right? We have another table. And how many rows do we have? We need to combine all the rows together, right, if we calculate the product first. In other words, the number of rows will be 2 times 4 will be 8, right? And based on the product between these two relations, we further apply the selection based on the condition that sales.bar equals to bar.name. In other words, among them, we further do the selection to select some rows, and we can represent the result at the bottom. The schema will be the combination of all the attributes for bar and sales, right? We have bar, beer, price from sales table. We have name, address from bar table, right? And for the data tuples, before we mentioned, if we calculate the product between them, the number of rows will be 8. 2 times 4, right? However, if we further apply the condition for the selection here, then we can further prune some rows and also delete the remaining ones. And we can check the remaining rows we have in the table. Each row denotes a data tuple, right? And we check the bar name. We check the sales bar versus by name. We find that each one they are equals to each other, right? AGH, Michael's pub, as well for the remaining one, right? So this is about Theta Join. Theta Join is defined by combining the product and the selection. If you can remember the basic operation that we covered before, then you should be able to follow the ideas we mentioned here very easily, right? So we do the product first and then further apply this selection.